we are now inviting Dr. Hashima Hasan ma'am, Deputy Program Scientist, NASA Headquarters. So before she speaks, I would like to introduce Dr. Hashima Hasan ma'am. So Hashima Hasan ma'am was born in Lucknow, India, where she got her early education and earned her BSc degree from Lucknow University. Ma'am has also got her MSc Physics from Aligarh Muslim University and earned a gold medal. She has been on the faculty of the University of Pune and a researcher at the Tata Institute for Fundamental Research, Bhabha Atomic Research Center, Duke University, US Environmental Protection Agency, and Space Telescope Science Institute. She has received numerous professional awards, including a NASA Exceptional Achievement Award. So, with us today, we have an exceptionally talented woman, Dr. Hashima Hasan ma'am. We are privileged to hear from you, ma'am. Over to you, ma'am. Thank you.
Thank you, Trishna, for that kind introduction. And Dr. Sharma, Dr. Ansari, and Dr. Zahid Hussain, it's an honor and a pleasure for me to be here today. I wish I could be in Meghalaya in person, especially after hearing all the wonderful work that is going there, but maybe one day I will get an opportunity to visit it. So if I may share my screen, I have a presentation for you. Today is to quickly share with you a personal journey of mine where I have actually worked directly with NASA's Hubble Space Telescope, which was launched in 1990, and the James Webb Telescope, which was launched in 2021. So my road to Hubble and JWST actually started, as has been mentioned, in Lucknow, where I was born soon after independence. And at that time, the skies of Lucknow used to be dark and clear. There was no air pollution or light pollution. And as a little girl, I used to stare at the stars and the moon and wonder where they came from. And I was introduced to the space age when I saw Sputnik go like a shooting star in the early dawn sky of Lucknow. Now, the girls' school that I went to, Loreto Convent, did not, at the time that I entered the school, they did not offer science in high school to the girls. But I was fortunate that by the time I reached class 9, science was introduced, and we were the first batch in the school to do science. I pursued it with a passion, completed my bachelor's at Lucknow University, and then went for a master's in physics at Aligarh Muslim University. And at that time, there were only 3 of us girls in MSc Physics at Aligarh University, including my dear friend, Dr. Zairun Nisa Begum, who is in the audience today. And she had come all the way from Assam to Aligarh to pursue her passion of science. And I used to be always so impressed with her. I had come only from Lucknow, but she traveled all the way left her home in Assam to be in Aligarh so she could do science. So, we have had dedicated women who have been really fascinated and pursued their passion for a long time. And I hope that there will be many more like that. So after completing my MSc and MPhil, I got a Commonwealth Scholarship to the University of Oxford in the United Kingdom, and I completed my doctorate in theoretical nuclear physics. And then I came back to India. So my road to NASA really took many turns. I did research at the Tata Institute of Fundamental Research in Bombay, as Mumbai was called then, and got my dream job at the University of Pune. Now, I must say that my family had been very supportive of me as a girl child, and then as a young woman, I was allowed to pursue my interest in science and to go abroad as an unmarried woman to do my PhD, and then go for a science career and becoming an assistant professor at the University of Pune. But even my family had, their patience also had limits. And with their blessing, I got married to a scientist at the National Institute of Health in North Carolina, United States, and followed him to Durham, where I continued my research in nuclear physics at Duke University, and then I got a U.S. National Academy Fellowship at the U.S. Environmental Protection Agency in North Carolina to do research on atmospheric science. We came back to India for a short period for personal reasons. I joined the Bhabha Atomic Research Center and then returned to the United States, where I found myself in Baltimore. And by that time, we had 2 infant sons as well. I was nevertheless determined to continue my career in science, and I was hired by the Space Telescope Science Institute in Baltimore to write the simulation software for the optics of the soon-to-be-launched Hubble Space Telescope and its science instruments. So that was my introduction to Hubble, and I later joined NASA headquarters. So Hubble, as we all know, is an iconic astronomical observatory, which has spectacularly extended our understanding of the universe. From nearby planets to the most distant universes, these discoveries have raised new questions, tantalizingly beyond its capabilities. And the James Webb Space Telescope will work in synergy with Hubble to continue and expand its scientific discoveries. Webb is really a technological wonder which will enable humankind to unlock mysteries of formation of the early universe. It's a tribute to the ingenuity and creativity of the human mind. With its 6.5-meter primary mirror and 4 powerful science instruments, it will study the first stars and galaxies, atmospheres of extrasolar planets, and learn where elements that form life came from, and much more. And in fact, it has started this scientific journey for us. Hubble and now James Webb are a part of NASA's great observatories, the other being Chandra, named after the Indian scientist Chandrasekhar, or I should say the Indian-American scientist, which is an X-ray observatory, and Spitzer, which has now completed its mission. It was an infrared observatory. And why do we need to observe in all the wavelengths? And that's because we expand our view of the universe. As an example, here you can see on the upper left-hand side is a Chandra image of the Crab Nebula. And the X-ray vision of Chandra takes us right into the heart of the nebula and shows us details around the around the central pulsar. And it has the X-rays have enabled us to see to follow the motion of particles in the bright ring over 20 years. On the right-hand side, upper right-hand side, is a Spitzer image of a star Zeta Ophiuchi, which is shrouded with dust. But the infrared light penetrates the dust, and we can see that the hot winds are blowing this dust and creating a bow shock. On the lower left-hand side is a Hubble image of the Ring Nebula, which is a dying star throwing out shells of gas and dust. And the Hubble images show greater details than ground-based images have shown of the expanding layers of dust. And on the lower right-hand side is a composite image of Hubble, Chandra, and Spitzer of 2 interacting galaxies known as antennae galaxies. And here you can see all the different reactions and what goes on when two galaxies collide. And in fact, one can see the entire life history of massive stars, right from their birth in gas and dust clouds to ending up as a X-ray object, an object emitting X-rays. Now, let's do a look back at Hubble. This was a bold vision for Hubble, which required it to be launched on the space shuttle, be serviceable by astronauts, and the science instruments could be changed, and so Hubble could be kept current. And this is a Cassegrain telescope with a 2.4 meter hyperbolic primary mirror and a secondary. And its science instruments operate in the ultraviolet, visible, and near infrared. It's in what is called a low Earth orbit at 545 kilometers, orbits the Earth at a speed of 28,000 kilometers per hour, which means that it completes an entire orbit in just 97 minutes. Now, I want to say something about the Hubble primary mirror. This is made of lightweight glass, and it's a honeycomb structure, so it's not solid, so it can be light. It's got a coating of aluminum and magnesium fluoride, so it can reflect ultraviolet light. It's the smoothest mirror which has ever been ground, but there was a problem with the Hubble mirror. The edges of the mirror were ground to the wrong shape, and we did not realize it till Hubble was launched. So here's a ray diagram of how the light goes first to the primary mirror, then to the secondary, and then it focuses behind the mirror into the science instruments. Now, because of the flaw in the mirror, the focus wasn't sharp as was expected, as shown in this diagram. And when we got back the images, you can see two on the top. The images were blurred. There weren't sharp points. And in addition to that, the focus changes were introduced as water was desorbed from the graphite epoxy truss, which is a frame supporting the mirrors. On the right-hand side, you can see that frame, the graphite epoxy frame, which supports the primary and secondary mirrors. And normally, we knew that it would desorb water in space. What we didn't know how it would dissolve, but we also, had there been no spherical aberration, that would not have caused so much of a problem. And that's where I came in. The Space Telescope Science Institute appointed me as the instrument scientist, and it was my job to use my software and develop it further and analyze the images of Hubble and characterize the error so we could design a fix for it and keep the Hubble, what we call, in best focus. And as I mentioned, because the truss was desorbing water, the distance between the primary and secondary mirror would decrease ever so little, but because of the error, it would cause even further aberration of the images. So it was my job to keep it in focus. And so I worked with the team to design the fix. And in the first servicing mission in 1993, the Hubble optics was fixed with the what is called a COSTAR, corrective optics for space telescope axial replacement. And this was basically an instrument which little mirrors were placed in front of the instruments, and these corrected the aberration of Hubble. And here you can see how the Hubble examples of how the Hubble images were corrected after COSTAR was employed. And since then, of course, Hubble has been doing spectacular science. learning about birth of stars, galaxies. It determined dark energy, for which there was a Nobel Prize. It measured the atmospheres of extrasolar planets. It has observed the further stars, and the list just goes on and on. And if you're interested in the timeline of Hubble development, here's the website, or NASA website, which shows the development from the time it was first proposed in 1946 by Lyman Spitzer till its launch in 1990, and it's still going strong. After Hubble was fixed, I decided I wanted to do something different, and I got a job at NASA headquarters as a program scientist. In all the years I've been there, I've been a program scientist for over a dozen missions, spanning the entire wavelength from X-rays to ultraviolet to infrared, to visible, infrared, and even gravity. I was the program scientist of Gravity Probe B. And the missions which are highlighted in yellow on this, I'm still program scientist of. And I'd like to mention this picture on the lower right-hand side, where I'm standing with a group of teachers which flew aboard the Stratospheric Observatory for Infrared Astronomy, for which I was also program scientist. That observatory has now finished operation, and we mounted a telescope provided by the German Space Agency aboard a 747 jumbo jet, and that used to fly and take observation. And we used to take teachers over there so they could learn how scientists do research in a flying observatory and take that experience back to their students. So the Webb telescope is Hubble's scientific successor. It studies every phase in the history of the universe, from the creation of first light, assembly of galaxies, birth of stars and planets, and also planets within our own solar system and the beginning of life. So it will be able to detect, and it has already started detecting and studying the formation of the first stars and galaxies created 13.6 billion years ago. And it follows the evolution of these galaxies, studying black holes, capturing light from them that stretch into infrared. And this infrared capability enables us to see in the birthplace of stars with much better detail than Hubble did. And it will study how planetary systems form and evolve and discover extrasolar planets, that's planets around other stars, and see if there's habitability out there. And it will observe gas giants in our own solar system and study their weather and climate, as well as Kuiper belt objects and asteroids. Webb's specialization is in the infrared. And to remind you, here's the electromagnetic spectrum, of which visible is a very tiny part. And the Hubble Space Telescope observes in the ultraviolet and visible and a little bit of the near infrared. But Webb goes right from infrared to the mid-infrared, and Spitzer went from mid to the far infrared. And as I mentioned, we have observatories in all the other wavelengths. And the reason we go into space with these observatories is because a lot of these wavelengths don't penetrate the Earth's atmospheres. And even those which do penetrate don't do it, are obstructed by the Earth's atmosphere. So that's why we need telescopes in space. Webb can peer through and examine dust. And as an example, here are some images in visible and near infrared taken by Hubble and by mid-infrared by Spitzer. And you can see in the visible image in the far left side, the newly born stars are not visible because they're covered with dust. But in the infrared image, the dust goes right through the, the light from the stars, infrared light from the stars goes right through the dust, and you can see the newborn stars. And on the right-hand side is a mid-infrared image from Spitzer, and mid-infrared is emitted by dust. So you can see the dust columns being dissolved with the hot light of the newborn stars. So infrared light gives us a lot of information. So here's an image of Webb, of that same Eagle Nebula that we saw in the last image. And here you can see much more details than before. We can see newly born stars in the dense clouds. And we can see the columns of interstellar dust, which at times look semi-transparent in near infrared light. And the wavy lines at the edges of the pillars are ejections from stars that are still forming in the gas. And we can see a glow which comes from the energetic hydrogen molecules that result from jets and shocks. So we are seeing more detail from the Webb image than we saw from the Hubble image. Here's another Webb image showing a planetary nebula, which is the Southern Ring Nebula, also this has been taken by Hubble, but Webb is showing us far more details. And the left image is in the near infrared, and the right is in the mid infrared. And we can see that there are actually two stars which are orbiting each other, which are causing this nebula, throwing out these rings of gas and dust. And on the right-hand side in the mid-infrared, you can see the second star also, which has been shrouded with dust. And it's the dimmer star which is throwing out these shells of dust. And the brighter star will also start doing that as it dies. And from these shells of dust, the astronomers can learn a lot about what is going on, when stars die. And they can study, the different shells are thrown out at different times. So the outer shells were the ones which were thrown out first, and the inner ones were thrown out second. And they can learn a lot about death of stars and how the interstellar medium, that is medium between the stars, it gets enriched with materials thrown out by stars and forms material for new stars and new planets. So another aspect of the light is that it travels, as it travels, it stretches. That's because the universe is expanding. So the light which started as blue and ultraviolet and blue light from newborn stars has now reached the infrared. So if we want to see the first stars, we have to observe in infrared, which is what Webb does. Another tool for the scientists is not only images, but spectra. So we also send up spectrometers in our space telescopes. And here is an example of a spectrum of this Southern Crab Nebula. And by studying the spectrum, not only do we know what elements are contained in the object we are studying, but the scientists can determine the speed of the objects and many other aspects of the object. So spectra provide a lot of information and are a very important tool. So let us remind ourselves of the history of the universe from the time of the Big Bang, which was 13.8 billion years ago. And it's called the Big Bang, not because there was a big loud sound, but because there was a sudden expansion. The entire mass and energy of the universe was concentrated in a very small point called singularity, and that singularity suddenly started expanding. We don't know what caused it, but we know it suddenly started expanding. And then the universe was filled with elementary particles, and no photons could escape. Astronomers call that period the Dark Ages. And then the neutrons and protons started electrons and protons started combining to form neutral hydrogen gas. And the gas then started forming clumps because of gravity, and nuclear reactions started taking place, and first stars were born. And we think they were formed 400 million years after the Big Bang. And then galaxies were formed, and our sun was formed 9 billion years after the Big Bang. So it is these first stars and galaxies that the infrared vision of Webb will enable us to see. So it's really very exciting. We see the first stars and galaxies forming in addition to details. So here is one of the first images of Webb that was released. It's called the Deep Field, and here you can see far more galaxies than Hubble has ever seen. And you can see that there are, what looks like streaks. These are gravitationally lensed galaxies. When there are a galaxy, there's a whole clump of galaxies and there is a galaxy behind it, the light from the galaxies behind is bent by gravity by the clump of galaxies in front of it, and it forms an image. But the images are distorted, and the astronomers can put them together to get an image of the galaxy, which is hidden behind the larger clumps and is further behind. So this way we can see galaxies which are really, really far away. And here is an example that the astronomers have already started analyzing this deep field. And here's an example of this one little teeny patch you can see on the left-hand side, this yellow triangle, which is enlarged on the right. This is known as the Sparkler Galaxy, and you can see the contrast between Webb and Hubble. And those little circles around it, one which is blown up and put on the lower right-hand side, they are globular clusters, which are bunches of stars. So we are beginning to see details of this level in Webb images. And as the astronomers start analyzing it further, we'll start seeing more details and learning more. Here as an example of the furthest galaxies that have been seen in the Webb images. The astronomers analyzed about 250 galaxies from that deep field, and out of them they found 4, which are, I would say, about 300 to 400 million years after the Big Bang. So they used a technique called Lyman break, where they look at the spectra from these galaxies, and from that they are able to determine how far they are, how far back in time they are. And the images are in the center in these little boxes. So this is really amazing to be able to see galaxies so far back in time. And this is just the beginning. Here is a composite image of the near and mid-infrared again, this is an interacting galaxy called the Cartwheel Galaxy. The little red galaxy on the left-hand side has gone through the center of this galaxy, the big galaxy on the right. And this galaxy has also been imaged by Hubble, but here we begin to see a lot more details. We see star formation regions in the outer ring, newly formed stars, and older stars are in the center part, and you can see it's kind of very smooth. And we can see dust lanes from the mid-infrared. So the red part, whatever's marked red in here represents the mid-infrared. So we see the dust forming over there. And as astronomers start studying the details of this galaxy, we will learn more about how galaxies evolve when they interact in this way. And here is another galaxy. This is in the mid-infrared. And in the mid-infrared, you start seeing the dust. And so this is a spiral galaxy. And now we can see how much dust there is in the spiral arms and how it is spread. And the center part is where the star is, and there's not much dust there. So you can see the star over there. So this is just an example of the kind of science that is beginning to come out of Webb. Here is another set of interacting galaxies called Stephan's quintet, and the reddish cluster in the middle, that's where newly born stars are coming. And infrared light also helps us find distant planets. And this image is really a ground-based image where in infrared, the central star is very dim, and we also can block it out with a disk, which is called the coronagraph, and the infrared light shows the planets which are bright in infrared. So Webb has taken its first image, direct image of infrared, of extrasolar planets, that again, planets around other stars. So this is just a demonstration of its capability and the clarity with which it can take an image of a planet, a direct image of a planet. So this is a really very exciting thing that we can now start taking images of other planets around other stars. It will also look at, decode the atmospheres of planets. Here is a simulation of the Earth's atmosphere. If a telescope were to look at the atmosphere of the Earth and take a spectrum, this is what it would look like. And Webb has already taken spectra, and I will show you that, but here it shows that Webb has discovered a rocky planet, which is the size of an Earth. So maybe there's another Earth out there somewhere. And this is done by a technique called a transit technique, where the stars, when the planet passes in front of its star, the starlight gets dimmed. And from that dimming, one can measure the mass of the planet, the size of the planet, the orbit, and you can get a lot of detail. And we have also measured the transmission spectrum. So as it passes, the light of the star passes through the atmosphere of the planet, we can take a spectrum, and these white dots in the graph on the right-hand side show the spectrum of the star, but it is very flat. And the green line is a simulation that if there was methane on the planet, that's what the spectrum would look like. And the purple shows that if there was carbon dioxide, that was what the spectrum looked like. But the spectrum doesn't look like anything like that. So this particular planet doesn't seem to have an atmosphere. But on the other hand, there's this planet WASP 39b, which does seem to have a very rich atmosphere with water, potassium, carbon monoxide, sulfur dioxide, and the one that was most exciting discovery for the scientists was sulfur dioxide, because that is typically formed when light interacts with something. So its photochemistry produces sulfur dioxide, and on Earth it's produced, for example, in photosynthesis or in creating the ozone layer. And by studying the details of these molecules in different parts of this atmosphere, the astronomers can start understanding how the planet was formed, where it formed, whether it was formed close to the star, far from the star, and so on. And so they're beginning to do these analyses. We can also re-examine the larger planets in our own solar system in near infrared light. And here's one of Jupiter. And you can see the aurora, the bright aurora on the poles. And that's caused because of the height of the atmosphere at the poles. And similarly, you can see on the belt and the red spot, they're looking white because they're reflecting the sunlight, and also because the atmosphere is quite high. But when there's no atmosphere, then you see the black lines. And so one is beginning to get a lot of details of the atmosphere on Jupiter from this. Webb has also been used to study the moon of Saturn and tracking the clouds over the moon, which gives us an insight on how the air is moving on the Saturn's atmosphere. And the top image is a Webb image, and the bottom image was taken with the Keck telescope in Hawaii a few days later. So you can see how the different clouds are moving on that atmosphere. And since this is the only moon in our solar system with a dense atmosphere, as the only place besides Earth to have present-day liquid rivers, lakes, and oceans, it's important to understand Titan's environment. Webb has also viewed Mars. On the top right-hand side, we can see it's dominated by infrared light, and the details are similar to the visible light image on the left, which was taken by the I think the Mars rover or the Mars orbiter. And then the lower right image shows the thermal image in mid-infrared, and the brightest region is where the sun is nearly overhead, and it decreases towards the pole. And as the light is emitted by the planet, it passes through Mars' atmosphere. Some gets absorbed by carbon dioxide molecules. And the Hellas Basin, which is the largest well-preserved impact structure on Mars, spanning more than 1,200 miles, appears darker than the surroundings because of this effect. So it's not just the brightness, but the presence of carbon dioxide, which absorbs some of the light. So that was just an example of some of the science that is beginning to come out of Webb. So I'm hoping to whet your appetite for the science of Webb, and there's much more to come. And so we're looking forward with great excitement. So let me say something about the telescope. So this was led by Goddard Space Flight Center in Maryland. It's an international collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, and the prime contractor is Northrop Grumman Space System in California. For the 5 science instruments are the near-infrared camera, which is provided by NASA, University of Arizona, near-infrared spectrograph, ESA, mid-infrared instrument, which is a partnership between NASA and ESA, fine guidance sensor, and the near imaging spectrographs are contributed by CSA. Right-hand side shows a cartoon of the telescope. It's composed of 18 mirror segments which fold back, and it's protected from the heat of the sun and the Earth by a 5-layer sun shield the size of a tennis court. And there's a secondary mirror which comes, which is in front of the primary, and there's actually a tertiary mirror as well. So it's what is called an astigmatic system with 3 mirrors. Okay, so this is a comparison of the size of the Webb mirror and the Hubble mirror. Hubble mirror is 2.5 meters, Webb is 6.5 meters. So mirror is really the heart of a telescope. You can think of it as a light bucket. The more light a mirror can collect, the fainter objects it can see, and the more details it can see in an object. So Spitzer mirror was only 0.85 mirrors. So is one reason why this telescope is so much more powerful than the other. It just collects just that much more light. So this mirror is made of beryllium because it is stable under different heat conditions. It's light and it's very strong, doesn't break easily. And it is, so here on the right-hand side, you see one of the 18 hexagonal mirror segments. And in this video, this is a time-lapse video showing the different, showing all the pieces of the mirror being put together on the back plane. So in a Goddard Space Flight Center. So the mirrors were constructed in a different part of the country and then coated elsewhere. I mean, this telescope has been built all over the place. And then they were all brought to Goddard Space Flight Center in Maryland, where they were put together robotically. And so here you see, one by one, they were all put together. Segments remained. Once they were put, the mirror was in place. So after the mirror had been put together, they displayed it for everyone to come and see. And here I am standing in front of the viewing window of the clean room at Goddard Space Flight Center. The mirror is coated in gold to optimize for infrared. So the other big technological feat was the 5-layer sun shield. It has an SPF of 1 million. It's made of Kapton with aluminum coating and with doped silicon on the sun-facing side so that, you know, it can reflect the sun's light. And the temperature on the hot outermost layer is 230 degrees Fahrenheit, whereas on the cold side, it is minus 394 degrees Fahrenheit. It's important to keep the telescope cold because we don't want the infrared light from the surroundings and to interfere with the infrared light of the objects that we are trying to view. So here is a time-lapse video showing an engineering model of the sun shield at Northrop Grumman. We first made an engineering model to test not only the material, but to see if the sun shield could actually be made into 5 layers. It could be stretched and separated. And so this is the engineering model. You can see the 5 layers have been put. Now they are being stretched. And there are little motors there which make it move up and separate them. So they're being separated first, and then they will be stretched. And then here it is ready. So here's the engineering model. And so just let me speak a little bit about the 4 powerful instruments, which specialize in different areas of science that they're expected to do. So the near-infrared spectrograph will study is in fact studying the many distant faint galaxies. The near-infrared imaging slitless spectrograph will study the composition of exoplanets' atmosphere, observe distant galaxies, and examine bright objects that are very close together, The near-infrared camera studies the earliest stars and galaxies in the process of formation, young stars in our own Milky Way, and objects from distant regions of our solar system. It can also track the moon of extrasolar planets, as we have seen, as they orbit the stars. And the mid-infrared instrument studies the cooler objects with debris disks around stars, which emit most of their light in the mid-infrared, as well as extremely distant galaxies whose light has shifted into the mid-infrared over time. So here, the full telescope and the sun shield have been integrated. And here it is in Northrop Grumman. And here is a cartoon showing how the telescope is folded up and placed into the nozzle of the rocket, ready to be launched. And on the left-hand side, showing the nozzle on top of the rocket. The rocket was provided by the Ariane company, which is a French company, and it's a European Space Agency contribution. And so Webb was launched on December 25 of 2021. It is in an orbit 1 million miles from the Earth. And here, next one is a video showing the launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So it was launched from French Guiana,
This.
from the spaceport over there. And this is a video which shows the the Webb unfolding sequence. And you can see first the sun shield will unfold. It will first be stretched out, just as we saw in the test. And then each layer will be separated and stretched out. And we saw first the high gain antenna came out to communicate. That was the first thing that came out. And then the sun shield came out to provide power. And now the secondary mirror will come out, and then the primary mirror. So this was the sequence which happened in space, and it took 1 whole month for the entire process for getting into space and getting deployed. It's not, how do I stop it? Okay, so where is Webb's orbit? As I mentioned, it's 1 million miles from Earth at a point called L2. It's a semi-stable point, Lagrange point, where the gravity of the sun and the Earth and the moon almost balance out. And so this is a very good point for a telescope, and there are many telescopes there. So Webb orbits this point, and so orbits the Earth and orbits the sun, not the Earth, sorry. And it orbits the sun as the Earth orbits the sun. And here it gets an unobstructed view of the sky. Unlike Hubble, the view of Hubble is blocked by the Earth every time it goes beyond the Earth. But at L2, Webb gets an unobstructed view of the Earth. Of the sky. Also, it's far enough from the sun so it can be kept cool, but it's close enough to the Earth so we can communicate with it. And how do we communicate with Webb? We communicate with it through what is called the Deep Space Network, which has stations in California and Goldstone in Madrid in Spain, and in Canberra in Australia, and then those commands are sent to the Space Telescope Science Institute in Baltimore, which is the command center and operation center for the telescope. And the commissioning took about 6 months. First with the arrival at L2, which took about a month, and then it took time to cool down, which is also, I think, about a month. And then the telescope had to be aligned, instruments had to be calibrated, and after that, only the first images were taken. Here is a picture of the command center of Webb in Space Telescope Science Institute, where the operation of Webb is done from. And these are the first images which came out on July 12 of 2022. And all the data from Webb is archived in the Mikulski Archives of Space Telescope in Baltimore. It is free to the public. Anyone can go and get the data and analyze it. Even you can analyze it. So I hope some of the astronomy students in the audience will get this data and start analyzing it. Or if you are still, studying, once you are ready to analyze, the data is there. It's not going anywhere. So this is everyone's telescope. I hope you all will enjoy it. And finally, oh yes, and then here is the website where you can go get a lot of information on the web. And here are some more websites. And finally, I'd like to end on a personal note. And the picture on the left, I am with Nancy Roman, who is considered the mother of Hubble Space Telescope, because she was the program scientist and the head of astronomy at NASA headquarters, who made it possible that Hubble could be developed. And on the other scientist is, on the right-hand side is Nobel laureate John Mather, who's the project scientist of Webb telescope. And with him, I work almost every day. So he's a wonderful person. And in the picture on the right, I am with the NASA administrator, Charles Bolden. He was an astronaut, and he was the pilot of the Space Shuttle Discovery, which took Hubble up in the mission STS-31. And so he launched and deployed Hubble. So this was, again, a personal connection with Hubble and Webb. So thank you.